In 1962, a team of Danish archaeologists pulled 5 ships from the mud of Roskilde Fjord in Denmark. The ships had been deliberately sunk there, scuttled, filled with rocks, and pushed to the bottom, approximately 900 years earlier, used as a barrier to block the fjord channel against naval attack. They had been sitting in the mud for 9 centuries. When the archaeologists lifted them and began the painstaking work of reconstruction, piece by piece, plank by plank, iron rivet by iron rivet, what emerged stopped the entire field of maritime archaeology, not because the ships were well preserved, because of what the ships were. One of the 5, designated Skuldelev II, was a longship, a warship, built in Ireland around 1060 AD from Irish oak, sailed to Denmark, sunk in a fjord to protect a harbor, 60 meters long. When modern naval architects began analyzing the design, they ran the numbers multiple times because the first results seemed impossible. A ship this size, built from wood with hand tools with no engineering calculations, should not be able to do what the design was clearly intended. The hull flexibility calculations alone took months to verify, because what the Viking shipbuilders had achieved was a hull design so mechanically sophisticated that modern naval engineers are still studying it, still learning from it, still finding principles in it that contemporary shipbuilding has not fully replicated. 1,000 years later, the ships that changed everything are still changing everything, and the secret behind them is something so simple, so elegant, so counterintuitive, that when you hear it, you will not believe it at first. They built their ships to bend. To understand why the Viking ship design was revolutionary, you need to understand what it was designed to survive. The North Atlantic does not move in straight lines. Ocean waves, real ocean waves, are complex, chaotic, multi-directional. A single wave is not a wall of water moving in one direction. It is a traveling disturbance that interacts with every other wave, creating pressure patterns that push and pull in multiple directions simultaneously. On a ship in open ocean, this means the hull is not experiencing a single force. It is experiencing hundreds of simultaneous forces, coming from different directions, changing constantly as the wave pattern shifts. A rigid hull, a hull designed to resist all these forces by being structurally stiff, has one fundamental problem. When forces exceed the hull's ability to resist them, the hull does not flex. It breaks, catastrophically, suddenly, without warning. This is not a theoretical problem. It is the documented failure mode of rigid hull construction throughout naval history. Ships built on the assumption that stiffness equals strength, and discovering in the worst possible place that they are not the same thing. The Vikings had observed this, not in engineering terms, not in the language of naval architecture, but in the language of men who had spent their lives on the water and watched what happened to ships that did not survive. And in the ships they built, they encoded a different answer. Not rigidity, flexibility, not resistance, compliance. Build the ship to move with the water, not against it. The clinker-built hull. This is the technical term for the construction method that defines Viking Age shipbuilding. Overlapping planks, each strake slightly overlapping the one below it, like the scales of a fish or the feathers of a wing. Fastened with iron rivets and sealed with a mixture of animal hair and pine tar. It looks from the outside like a simple construction choice. It is not simple. It is a design decision with profound mechanical consequences. When a rigid ship meets a wave, the force of that wave is transferred through the hull as a single structural event. The hull either resists it or it does not. There is no middle ground, no capacity to manage the force, no ability to distribute it across the structure in a way that reduces peak stress at any single point. When a clinker-built hull meets a wave, something different happens. The overlapping planks are not rigidly fixed to each other. They are fastened, held in relation to each other, but they retain the capacity to move slightly relative to each other, to slide, fractionally, along the line of overlap, to flex. Under wave loading, a clinker-built hull does not resist the force as a single structure. It distributes it. Each plank takes a portion of the load. Each overlap joint absorbs a small amount of the energy. The hull as a whole deflects, bends slightly, twists slightly, moves with the water, and in doing so never reaches catastrophic structural failure. Modern engineers call this distributed load management. The Vikings called it the way a good ship moves. But here is the detail that makes this genuinely extraordinary. The flexibility of a clinker-built hull is not unlimited. It is calibrated. The degree of flexibility is determined by the thickness of the planks, the spacing of the rivets, the width of the overlap. Change any of these variables and you change the flexibility profile of the hull. Too rigid, the hull cannot absorb wave energy. Too flexible, the hull cannot maintain its shape under sail load. The Viking shipbuilders found the specific combination of variables that produced a hull flexible enough to survive, while rigid enough for sailing performance, without equations, without testing protocols, without any of the formal tools that modern naval architecture uses to solve exactly this problem. They found it through generations of building ships, sailing them, observing what happened and adjusting. Through the accumulated knowledge of masters, a chain of expertise stretching back far enough that no single person could have told you how it started. It just worked. And they knew it worked because the ships that embodied it came home, and the ones that didn't embody it didn't. The flexibility of the hull was the foundation, but it was only the first layer of what made Viking ships extraordinary: the keel. Every Viking longship was built around a single massive piece of timber, running the entire length of the vessel from bow to stern. Split, not sawn, from a single straight-grained oak tree along the natural fiber direction, preserving the structural integrity that sawing destroys. The keel was the spine of the ship, and like a spine, it was not rigid. It was designed to flex in the vertical plane, to bend slightly as the hull moved through waves, while maintaining its lateral stiffness. Modern biomechanical engineers would recognize this immediately. It is the same principle that makes the human spine both structurally strong and dynamically flexible. The Norse shipbuilders did not know biomechanics. They knew what a good keel felt like when they found the right tree. The shallow draft. A Viking longship drew, at most, 1 meter of water when fully loaded. 1 meter. A ship that draws 1 meter of water can go places no other vessel of comparable size can go. It can navigate rivers. The major river systems of Europe are navigable by a vessel drawing 1 meter for hundreds of miles inland. While merchant vessels of other cultures required port facilities, Viking ners were unloading cargo directly onto beaches from Iceland to Baghdad. Look at a Viking longship from above, and you see something most ship designs do not have: perfect front-to-back symmetry. In a narrow fjord or a river channel where turning a 60-foot vessel is impossible, the Viking longship simply reverses. A loaded Viking longship carried its weight low. Weapons, provisions, trade goods, all stowed below the rowing benches, as close to the keel as possible. Heel it to 60 degrees further than almost any seagoing vessel can safely go, and it still returns. It does not like to die. The square woolen sail was made of wool treated with animal fat that made it naturally water-resistant. Wet wool is almost as strong as dry wool. In a North Atlantic environment, a woolen sail was not a compromise. It was the only material that worked. The sails they produced were, for their specific application, superior to almost anything that came after them for centuries. Here is what the engineering genius of the Viking longship could not prevent. The thing that made it extraordinary also made it lethal. The flexibility that allowed the clinker hull to survive North Atlantic conditions also meant that the hull was never completely watertight. The overlapping planks that distributed wave load also allowed water to seep through the overlap joints, slowly, continuously, inevitably. A Viking longship leaked, not catastrophically, not in a way that would sink it quickly, but continuously, persistently. Every hour at sea, the hull emitted a measurable quantity of water. This was known, accepted, managed. Every Viking ship carried a bailer, a wooden scoop used to remove water from the bilge, and bailing was a continuous crew task, never stopping, never fully completed, just managed, for the entire duration of every voyage. Now combine constant bailing with the rowing requirement. A longship under oar power required its full crew rowing continuously. The rowing benches ran the length of the ship. Every man on board had a specific position and a specific oar. In rough conditions, the crew was rowing against waves, bailing constantly, and managing the sail if it was deployed. Navigating by environmental cues and doing all of this in a vessel moving in 3 dimensions simultaneously. Pitching, rolling, yawing, wet, cold, loud, for days at a stretch, without stopping. Because stopping, truly stopping, resting, sleeping in any meaningful sense, was not possible on open ocean. Someone had to row, someone had to bail, someone had to watch the horizon. Always. The physical cost of extended North Atlantic crossings on Viking crews was enormous. The sagas understate it because they were written for people who understood it. It was simply the reality of what North Atlantic sailing was. But read between the lines and it is there. The accounts of crews arriving and being unable to function for days afterward. The descriptions of men sleeping for extended periods after long crossings. Navigators were exempted from rowing duty because their function required a level of mental clarity that physical exhaustion would destroy. The ship could survive the North Atlantic. The men inside it paid for every mile. And sometimes, when the storms were too sustained, the bailing too constant, the men paid more than they could afford. The longship that came home was not always the longship that left. Sometimes it was a smaller crew. Sometimes it was no crew at all. Just a ship, somehow, still floating, found weeks later, drifting, empty, the most advanced maritime technology in the medieval world. And it still was not enough. Not always, not for everyone. In 2012, a team of Danish shipbuilders completed a project that had taken 10 years. They had built a full-scale reconstruction of Skjoldelev II, the 60-meter longship pulled from Roskilde Fjord in 1962. They used only Viking Age tools and materials, hand tools, split oak not sawn, iron rivets forged by hand, wool sails woven on traditional looms, pine tar and animal hair for caulking, no power tools, no modern fastenings, 10 years of work by master craftspeople studying the original ship, rebuilding the knowledge lost for 900 years. When the ship, named the Sea Stallion from Glendalough, was launched, the builders were not entirely sure what would happen, because knowledge and practice are different things. You can study a Viking ship for decades and still not know if it works. It worked. The Sea Stallion sailed from Denmark to Ireland in 2007, retracing the original 900-year-old route, 1,400 nautical miles. Open North Atlantic, with a crew of 65 people who were not Viking Age sailors. And still, the crossing was brutal. The accounts describe the physical reality in a way no academic paper quite manages. The cold that does not leave your body. The constant, overwhelming noise of water and wind that makes it impossible to think. The bailing, always the bailing. The moment when you start thinking only about the next hour, the next wave, the next bail. And then, after weeks at sea, after everything the North Atlantic could produce, the coast of Ireland appeared. The same rocks, the same hills, the same smell of land after weeks of nothing but water. A crew member wrote she finally understood why the Vikings kept coming back. Not for gold or land, but for this. For the confirmation that the ship worked, that the design was right, that the knowledge passed through generations was true. The ship that was built to bend did not break. It was built to move with the water, not against it. The ocean does not reward rigidity. It rewards compliance, the willingness to flex and give way without losing your shape, without losing your way home. The longship is still in Roskilde today. 60 meters of split oak and 900 years of water, still telling the same story. Build to bend, move with the water, and the water will carry you home.